Hey guys, welcome to the Abaqus part for this video on deep drawing. So this video will be only on the setup of the model. So for all the explanations, I'll kindly refer to the video that comes in front of this one in this playlist, because there I really go into the theoretical details as well as the application part in Abaqus of certain aspects like the anisotropy and the orientation of the sheet and stuff. So this is just a quick setup to show you that it's actually possible, what I claimed in the previous videos. So let's get started right away. So in this case, you can see I used, and you can again see the naming here for my different models. I used the discrete rigid approach for my punch, as well as for my blank holder and my die, some refer it to as matrix. If you want to go, I just quickly go into this. If you want to use an analytical rigid approach, you are only allowed to do full revolutions. So if you get an error when setting up, let's say, quarter symmetric simulations with analytical rigid, keep in mind that this only applies to your sheet then. So your sheet can be just quarter symmetric with the given boundary conditions or the given the specific symmetry conditions. However, your blank holder, your die and your punch need to be 360 degrees revolutions. But anyways, just I wanted to quickly point this out. So starting out, as I said before, the blank holder, the die and the punch are all modeled and based on discrete rigid. So keep in mind that you have to mesh it. And again, you can see I performed some finer meshing here in the radius, because this is really important if you want to get the movement of the material around the corner right. So the sheet will be here, barely any movement of the particles of the sheet underneath the punch. However, it will bend around this corner, so having a good resolution of this edge is fairly important. And the same actually holds true for this radius, right? So this is the discretization of your circle, so to speak. So don't make it too coarse, because that might greatly affect your results. The same, or even more so, I would say this applies to the die or the matrix, right? So you can see again here the meshing of especially since it's an inner radius that's being meshed, this will definitely have a big impact on your results. So always keep that in mind. I would say never go below 5 or even 7. And in such kind of simulation, it's the more the better, because not only does it affect your results from a physical standpoint, but it can also cause some numerical issues if you go for very coarse meshing in this area here. So always use local seeding, as you can see here, to increase the density of the mesh in this area. And okay, if you would take a look at the mesh of the sheet, you can see I chose a very specific approach that I really like to use. So if you use just one section and do a sweep approach in a quad dominated fashion, then you will get triangular elements here around the center point, which are very, very small and tiny. So especially in 3D simulations, in 2D simulations maybe not as much, but in 3D simulation, these kind of elements that you will see, let's say the last row of elements, let's say if this is the first row of element, I call this the last row of element, they will consist of wedge or triangular elements in 2D. And so always keep that in mind. And so for instance, why did I choose this kind of meshing? Because the radius of the punch will be somewhere here. So in that swept area, in that area that behaves axisymmetrically. So I really encourage you to perform a simulation with such kind of a mesh, and the one that you don't using the sweep option. So which is like which consists of a mesh entirely like the inner radius. So you will see that just the choice of your meshing technique, if it's axisymmetric or not, so if you go for a free mesh instead, this will have an effect. Your results are very likely not to be axisymmetric anymore. So if you want to perform axisymmetric simulation using a non-axisymmetric approach, for example a full simulation like a 360-degree simulation, or in this case a 90-degree simulation, still keep in mind to use the axisymmetric mesh in that areas where it really matters. So underneath the punch, as I just said a minute ago, it doesn't really matter because their material movement isn't really strong. So there's not much happening. So most of the interaction inside the body, so the stresses propagating, is at the area where the sheet will bend around the corner of the punch up to the point in the wall and the flange area. So this is just something that I wanted to point out. We talked about the orientation in the previous video, right? So remember to check your element face normal, right? So as shown in the video, it was given here, and then you create a datum axis or a datum system accordingly. So I talked about this in all the details in the other video. Just wanted to show you how it would be done, right? So you create the datum system according to what you found out for your normal components, and then simply assign it, to the sheet. Alright, so that's very important, because otherwise your anisotropic material model doesn't know which directions you mean when you specify your anisotropy values for your Hill condition. So which are, as I've shown in the other video, based on your Langford parameters. So I pointed out some crazy, I've just called it crazy metal. We talked about also in the other video about the jump of the yield stress values, which is very steep in the first 0.05 section of your plastic strain. So keep that in mind, that you might want to choose a more realistic, higher resolution other than what Abaqus will do, which is linear interpolation. So you would define a sub option potential, which I already did. So we've calculated, I've shown you in the other video how to calculate these values. These are based on actual experimental values, and we will later see the effect of this, which is not very significant. So sometimes you think, okay, I've detected a fairly strong anisotropy, but then it turns out that in other than a simple tensile test environment, it doesn't really affect your results that much. So what I also did, just in comparison, I created a material that has some artificial values only for the purpose that you see they are significantly higher. And again, it's just R22, R33, which correspond to the two in-plane shear directions and the shear direction. However, these are, let's say artificially high, but this could be, or these could be values for a metal that actually exhibits a fairly strong anisotropy. And again, just because I was curious, I also created an isotropic material. So this is stuff that I like to do, just play around. I always encourage you to do it. Just create, out of curiosity, create a new material, create a new mesh, and so on, and just run the simulations and see how these changes affect your results, right? So, and in this case, we also talked about defining a specific shell thickness. And I guess what is really interesting was we also talked about this, the consideration of the membrane element thickness. We also talked about this, but let's just go on step by step. So there is just a pretty straightforward interaction between the blank holder and the sheet. We talked about the different approaches, how you can model a deep drawing process, just for the purpose of keeping it simple. I chose in this case a fixed displacement for the blank holder. So the distance between the blank holder and the die is always a known fixed value. So there is, I don't know, I think I just took 1 millimeter distance and the sheet was 0.8 placed in the center. So there was a 0.1 gap distance and 0.1 distance to the blank holder and the die respectively. So pretty much straightforward definition here. I like to do a lot of the things in one step because it is still the case that when you go for multi-step simulation, for some weird reasons, like switching from one step to the next, it might cause some weird error. So sometimes just doing all your operation in one step might actually solve some issues that you wouldn't be able to get rid of any other way. So this is still a bit weird. So we talked about the interaction, and so for the interaction properties, remember we talked about this. If you keep it empty, that like referring it to hard frictionless contact, whereas this might actually work better, don't ask me why, than if you actually specify a hard frictionless contact. So don't get confused by this empty window here. So contact control was another big thing that we talked about in the video, because especially if we do this in an implicit manner, right? So the people will just, because of the problems that the specific deep drawing operation poses as a, let's say, in terms of numerical challenges, the people will just automatically go for explicit simulation and say, yeah, go peep, and I don't want to deal with it. But I found it very interesting when preparing this video to see, okay, how at the time, back in the days when I prepared this, I didn't know about the contact controls, because before I was never forced or requested to use it. But this particular problem forced me to deal with it. So I looked into it, and this is, by now you should know the style I like to do, right? When you face a problem and with your current set of tools or your standard tools, you cannot fix it, there might be some advanced or extended option that you can choose in order to get rid of or get around the problem. And we talked about this in the previous video, and I found this pretty interesting. Learning about this. So this is why I presented you this in this video. So at the end, the stabilized implicit simulation is still much faster than the explicit one, which makes sense, because I mean, this is the reason why you still want to do implicit, other than, let's say, the physical accuracy. But in this quasi-static environments, your explicit solver will also lead fairly accurate results, because there is no unless you use a very high mass scaling, of course, right? When I say that the explicit solver will yield, or the dynamic explicit solver will give you very nice results, I mean, if you don't play around with like any of the density mass scaling. We talked about this in the ELLI explicit video, right? So that it's up to you how physical the results actually are. So yeah, so much for the contact controls. Of course, you know, I still like to work with an amplitude, like getting into contact using a fairly soft speed and then performing the actual forming operation. So boundary conditions. Here's a good example how not to do it. So when I reopened the CIE file, I was like, okay, what is this? I had to double click. Okay, it's the symmetry of the sheet in this direction, and then I went down. So always name your boundary conditions properly. So call this sheet symmetry edge in X direction and so on, right? So, and here it's fixing the blank holder, and this is the actual movement of the punch, right? In minus Y direction with a speed of 5 mm, right? So always properly name this so that you can, I mean, I don't know if I would call this a proper naming, but since it doesn't really reflect the actual material all the way down. So it's fine to call it a crazy metal with high anisotropy. So so much for the setup. So a short recap. What are the important things? Defining the potential given so that you can provide Abaqus with the anisotropic values and the orientation of the sheet, and then assign the section accordingly to the datum system that you've created, right? So that the material knows in which direction your material will behave anisotropically. So that's end contact controls, I would say, is the other big new thing in this case. So a couple of things we've changed compared to the previous videos, and you will find a lot of applications where, for example, the contact controls, if you want to go for an implicit simulation, which I recommend in most of the cases, right? The people are just nowadays, given the computational powers, I just don't care about most of the things, just let me do dynamic implicit, because it has no convergence issues, right? We talked about this in the video 6, right? But the physical accuracy of the results might be affected very well, or the computational time, if it's a non-high speed operation, right? If you for example model a machining process and the chip formation, that might be an interesting case where it's not very dynamic. However, it's a fast process, so the chip has a low mass, but it happens so fast. So then in this case, the explicit solver might actually be the better choice. But as you know, in metal forming, in many cases, the operation is not super fast and does not include as many inertia effects. I mean, we at the institute, we perform a couple of super high speed forming operations, like with vaporizing foils or electromagnetic forming. This is in these cases we always go for explicit dynamic simulations, because there sometimes even the dies tend to vibrate because the forces you apply or the dies apply on the sheet are not super high, but the time span over which you apply it is so short that your inertia effects really play a big role in the outcome of your simulation, up to the point where, let's say, your die can also fracture because of the huge impulse technically, right? It's a short amount of time. So if we look at the results, I just open up two results before this, and if we just look at the results, you see that given a standard and given the anisotropic values or anisotropy values provided in the previous video, you see the anisotropy is there, right? You can see in the stresses it's a little different. We can also check out that you see here there is a little bit of more plastic deformation compared to the left side. So there is a slight anisotropy to be seen here, and we can also, if we look at the magnitude, you will see, okay, you cannot really see it, but the values here would be slightly smaller than over here. So if you compare the value of this one in this direction versus the value of this one in this direction, there is a small difference. No, so it was u. So this value of in z direction of this element versus the x direction of this element, right? So anyways, this is not really what I wanted to point out. So let's go back to the von Mises stresses. What you again or also can see here is this small wrinkling. So if I go back in this view, you can hopefully see this small wavy pattern which manifests itself geometrically. So you actually have these kind of waves, but probably right away from the beginning you could see this pattern in the stress distribution. So it sometimes might be the case that it is not easily being spotted in the strains, which is of course the case here, but you would probably always see it very nicely in the stresses. However, in this case, even the strains clearly show this waviness pattern, but it really stems from the geometrical waviness of your sheet. So where does it come from? So we talked about this, that was the last part. I talked about this in the previous video, that you have this different definitions of your blank holder. And if you keep a certain gap between your sheet, and I'm talking, since we did not exclude the shell thickness, I mean the actual model thickness, which was 0.8, and whatever fixed gap there was between the blank holder and the die. It gives room for the sheet to show this wrinkling behavior, right? So this first order wrinkling. So because this is what the sheet wants to do. We talked about this, right? So you apply some compressive stresses because your ring segments are forced to move to smaller radius. So this induces compressive stresses in the meridional direction. I don't know if that's the correct term. And so this wrinkling is just a result of these stresses being induced. And whenever you give room for this movement, it will happen. It will happen. You will see this very early on, because this is just see, even here, you can already see this occurring, right? So from larger waves to smaller waves, and then you can already see it nicely happening. So if we compare this to a sheet that was, I just increased the anisotropic value artificially. No, okay, let's remove these two and take a look at this. And here you can also see what I talked about. So you can see that the segment where the radius is being formed underneath the punch is part of my axisymmetric mesh. So maybe it's a close call here. I could have extended the axisymmetric mesh, let's say up to here a little bit, to have a better, or to make sure that it really is a axisymmetric response if I'd use an isotropic material model. So, but here you can nicely see, if you artificially scale up your anisotropic values, then you have this typical earring, what you expect, right? You have a higher edge and a lower edge. And this is actually the case that, given the hill condition, it will always give you, let's say, two ups that would be on this side and over here, and two lows which would be over here, and 180 degrees across that low. So, but again, you can see maybe even more pronouncedly this waviness pattern. However, the geometrical waviness is again here also defined by the gap, the clearance that you leave between the punch and your die, right? So if this is different compared to the distance you keep between the blank holder and the die, then this will, the sheet will behave differently underneath the blank versus between the wall of the die, the wall of the matrix, and the punch, right? So I think there was even a little bit more space here, so you have this added extra waviness even in this direction. So not just in this direction, but also in here. So you can see that simulating with this fixed distance might not actually be what you do in reality, because usually the blank holder is force driven and you apply a constant force, right? So again, this is really a thing that you should play around with, and keep in mind that this heavily affects how the shape of your final part will look like. So as you can, I just wanted to point out one aspect here. So the reaction force in y direction from my reference point of my punch. I hope it loads. Yeah. So you can see this is everything but constant, right? And why does it look the way it looks? So at the beginning, there's not a lot of material that's been pulled towards smaller radius. Then you have the highest force required, let's say in the midsection of your process, and towards the end there is not much material in the flange region, so most of it is already drawn into the wall area. So you have this very, very typical pattern that you can also predict analytically quite well. So if you compare this to some basic lecture, this really shows this nicely. Another thing I wanted to point out is the one of the blank holder, which follows a similar path. However, you have a quite abrupt drop here at the end when there is no material between the die and the blank holder. But you can also see, so it has an increase over time. And the thing is that if you have an actual machine that you would have to control very specifically over time to really get to the same results. So what you do in reality most of the time, you just say, okay, I go for, like in this case, 10 kilonewton, right? So this is what you put into the machine, and it will push down the blank holder onto the sheet with a constant force of 10 newtons. So I would really like to think about to try out in an actual machine to give a non-constant function over time for the for the blank holder force, and see how this might affect my results. Because if the area underneath the blank holder gets smaller, we talked about this, right? So the actual contact pressure is increased if you give the same force to the blank holder all the time. So so much for the Abaqus part. I would really like to refer you maybe once again to the other videos where I talk about many other aspects, especially the energy related aspects. But this is what we wanted to have, a nice anisotropically drawn cup, so a cup that shows some earring. And I hope you liked that video. Please click like and subscribe, and see you in the next video. I'm looking forward. Take care, guys.